Hi, I'm Hannah Fleshler, and this is my presentation on gravity and air drag. In this lab, we analyzed an object that falls slower than a rock. This potentially means that it is experiencing air drag, but we wish to prove that with this lab. Properties, we use Newton's second law, aka the momentum principle, to predict where the object will be. We also evaluate the net force by determining the acceleration of the object due to gravity and then adding the force of air drag. Here's some of the equations I use: the velocity update formula, position update formula, the force of gravity, which is the negative mass times the gravity constant. The main result of the lab was the discovery that an object with a wide surface area experiences more air drag, and it could potentially experience terminal force. Since the model was only moving in the y direction, we could safely assume that the fnet of x and z were 0, so I only calculated fnet of y. Here's an image of my tracker. On the left, you can see I'm dropping a piece of paper, and on the right, you can see my graph. It is a relatively straight negative line. My system was a piece of paper, and the surroundings was Earth. The initial conditions were set to 0 velocity and position 0, since it dropped from a state of no movement, and 0 position just because it's the easiest to model. On the left is my gravity and drag code. You can see I calculated the force, the net force, with the force of gravity plus the force of drag. I found the force of drag using the square root of the speed. And on the right, you can see my gravity model. And I used just negative mass times gravity constant as my fnet, the y fnet, and all the others being 0, or x and z are 0. And then also for both of them, you can see the velocity update formula and the position update formula. Here's my just gravity function. You can see it's a downward sloping motion. As the time increases, the speed increases. And here's my gravity and drag graph, position versus time graph. You can see it's a straight negative slope, which is very similar to the observed position versus time graph as well. Here's it on all three on the same graph. It was a little difficult to do because the timestamps were different for the models versus the observed time. The observed time was had an incredible amount of timestamps, and also the video starts a little bit late and ends a little bit different, and it's hard to like keep them all the same. But yeah. And then potential errors. There's always potential errors when conducting a lab report. In this case, some include human error, like pushing on the piece of paper accidentally while I'm dropping it, or the timestamp error. It may have been better to try and use some smaller timestamps in GlowScript to adjust the graph, but it was very difficult to execute. All right, what does it mean? The velocity versus time graph for the gravity and drag model was a flat line, while the velocity versus time graph for the just gravity model was a straight negative line. Sorry, it was a curved negative line. This is because the gravity and drag model experiences terminal force. This results in the net force being equal to 0 as gravity and air drag balance each other out. Because the model and my object experience terminal force, they also have 0 net force and therefore a constant velocity. If an object was thrown instead of just dropped from rest, the terminal velocity would not be the same. In my models, I used an initial velocity of 0, But if the object was thrown, then the net force would have to be initial force plus gravity plus air drag, and the chances of air drag balancing out initial force and gravity is much lower. And that's all. Thank you for watching.